Hello, I hope you're having a good day. This is my Lab 5 presentation on high altitude freefall. So what's the purpose of this lab? Well, we'll be using an expanded drag equation to explore the relationship between atmospheric pressure, terminal velocity, and drag force. Our model is going to use the momentum principle and the constant update method to take account of all the forces, calculate a net force, and use that to adjust velocity and position. We're also going to show the impact of temperature on atmospheric pressure. So, some initial variables. So in this example, this is the Red Bull Stratos supersonic skydive. So a few variables we can assume are a man wearing a spacesuit is approximately 127 kilograms. This free fall took 260 seconds. That's from the time he steps out. It begins free fall until his parachute opens. And the real world data here was taken from the Red Bull Stratos POV video. And our starting altitude is 38,965 meters. Show a basic drag model and position update according to the momentum principle. This is similar to labs we've done before. We've got mass, position, calculating weight force, and then drag force with a B variable to make things line up properly. And then calculate Fnet from the previous two forces, and using Fnet to update velocity and velocity to update position, repeating that over and over again to run our model. So we're going to be expanding on the model of air resistance. So air resistance in the equation basically consists of air density, surface area, and drag coefficient. And last time, in the previous lab, we bundled that all into one variable called B. But we shouldn't expect surface area and drag coefficient to change very much during the fall, so we're going to leave those bundled into B, and we're going to expand on air density. So luckily, NASA has this handy-dandy set of equations to my left here that give a good approximation of what the air density will be at different heights. So what I did was learn how to do an if statement in Python, which is not as easy as I thought it would be, which will use these equations depending on the current model's altitude to give a good estimation of density. And of course, that's just going to plug right into our force of drag equation. So on the left here, we've got the computer model of position as they descend. And on the right here, we've got the actual data from the fall itself. They line up quite nicely. But what we're really interested here is speed. So as you can see, the speed peaks at a very high altitude when they've been falling for less than 50 seconds, and then starts to decrease as they go lower and lower. That's, of course, because as the diver goes lower and lower, the air is getting more and more dense, which means that drag force is increasing and their terminal velocity is decreasing. You can also see speed is never the same for long. That's because we're experiencing a non-constant force of drag. So why was air pressure so important? So on the left, we've got a model that represents what would happen to the speed if the terminal velocity of a skydiver who was just always at 5,000 meters. He's falling, but he's at the same altitude the whole time. And you can see he only reaches a speed of about 67.7 meters per second at that altitude, which you certainly wouldn't want to hit the ground like that. But it's not nearly as fast as the speed of sound because our coefficient of density at that altitude is very high. Meanwhile, at 35,000 meters, you've got a much lower coefficient of density, and you can hit a ludicrous speed of 660 meters per second. So as you can see, the best time if you want to go fast is, of course, at high altitudes. How did temperature impact pressure? Well, you can see over here in the equations that temperature and pressure are positively correlated. And this lines up with observations that, of course, high altitudes are both cold and low pressure. Like if you're hiking up Mount Everest, you're going to need a winter coat, but you're also going to need oxygen because as you get higher and higher, the air is less dense. We neglected several things to make this all work out nicely. First of all, surface area is actually not constant. Skydivers can become more streamlined or spread their bodies out in order to change their speed, but in here it's just a constant surface area. Gravity is in fact not constant. Gravity equals about negative 9.8 meters per second squared near Earth's surface, but it starts to decrease at higher altitudes. In this example, it's only about a few decimal places, but it is worth noting. And also, pressure is not exactly the same in density in all situations. However, it's they track linearly for the purposes of this lab. And I hope you enjoyed my high altitude lab, and if you ever plan to skydive from space, I hope it's a useful reference.